Okay, right now this is December 28th, Monday for me, but it's Monday, January 4th for you as you're working on this. Remotely in class or remotely at home. It should be keeping the same pace. And we left off with making these, which was a redox reaction, and we're going to stay on redox reactions this week for a while. I don't know how many days it's going to take at this point, because it took me a while to write these out. And then we'll jump back in the book, hopefully later this week. But what we're going to focus on for right now is balancing redox reactions. This is something that you should have some experience with. And to do this, we're going to be in the general chemistry textbook through the remainder of this flip chart, redox, which will go in your Schoology weekly notes as redox, sandwiched probably between Organic 2.6 2021 and Organic 2.7.2021. And also, if we go into Schoology, is this up while we're here? So, if we go to weekly notes, what I was saying is, this is here. Actually, this needs deleted and the new one printed and put here, but it should be here and then 2.7 after that. So we'll finish up redox. We did really all that section on the whole project that ended with the ornaments, and then we'll do some redox and we'll jump back into this book, hopefully later this week. But while we're here, videos should be in week 2.7. I don't have that done right now. And going back to here, what was I saying? Textbook chapters. This was chapter 23 from the physical science course. If we go into the general chemistry chapters, if you don't know where your book is at home or you didn't take a book home, that's all right. I am in chapter 19, which is the last one I copied out of there. And this is on redox. And that table that I showed you is in here. We might even do a little electrochemistry later. We'll take a little break because it's kind of fun and it's pretty easy. It's a little different. There's those redox rules. I blew past them somewhere. Okay. So these redox rules are on page 686 in that chapter. Table 2. And you need to be able to use the redox rules. When I was in college chemistry, you had to memorize the redox oxidation number rules. Oxidation number rules is what I meant to say. I doubt that they would do that today, but you never know. We use these in every redox reaction. And if you were trying to, for example, on an exam, balance redox reactions, you'd have to know these rules. You wouldn't have time to look them all up. You'd have to know your stuff. And by the way, in college chemistry, you need to read the chapters and read the material before you go to lecture, so when you go to lecture, you know what's going on, because when you go to take a test, you really need to know your stuff. Because you don't have time, there's a lot on there. So oxidation and reduction reactions always occur together. You can't have one without the other. It's any chemical reaction or process in which elements undergo a change in oxidation numbers or redox reaction. When an element is oxidized, its number goes in the positive direction. This could happen if electrons are taken away, so oxidation is losing electrons. When an element's reduced, the oxidation number goes in the negative direction. This can happen if electrons is added. So you probably know this is oil rig. We might have talked about this with some of the classes, but I'm not sure everybody. So let's take a look at this simple one. Sodium mixed with chlorine makes sodium chloride. You have to heat the sodium up and expose it to chlorine gas, and this will go. In this case, sodium is oxidized. It loses electrons. Chlorine is reduced. It gains electrons. And this is the balanced chemical equation. Now you have to get 2 electrons to cancel 2 electrons. And there's a whole process, multi-step process, to balancing these. This particular one is you know, a synthesis reaction. You can balance that without knowing the redox, how to balance redox reactions. But you can't do that all the time. Remember, while I'm on the topic of oxidation numbers, charges are 1 positive, 1 negative. Oxidation numbers are +1, -1. I write them in blue and they're centered over top. So they're not exact, they're often equal to charges. But they're not the same thing as charges. They're not written in the same way as charges. So remember, oxidation numbers are in blue, centered above, and with the sign and then the number. When it's written as a charge, it's the number and then the sign. An oxidation number is just a way of assigning a number to an atom. It's kind of like accounting. You're going to say that that atom has the capability to gain or lose a certain number of electrons based on that oxidation number. Writing it this way, by the way, these are called electronic equations. Now in class, we added I did this for one of the classes. We had iron 3 chloride in here. I had a test tube in here with a upside down with air trapped in it, with a paper clip trapped on it, clipped over the end, to use as a Cartesian diver when I squeeze this. And that iron 3 chloride, or in this case it was iron 3 oxide, was brown because the iron 3 ion is brown. And I took that out of there and I put HCl in here, and it dissolved that iron 3 oxide, and that iron 3 ion that's brown turned to iron 2 ion that is green. It's a very pale yellow green, so all that rust in there that got dissolved, you can't see that that's pale yellow green. A spectrophotometer could detect that if it was good. But in that case, that was a redox reaction. Your iron 3 ion gained an electron and became an iron 2. Chloride ion lost electrons to become chlorine gas and released electrons. So I have to have 2 electrons to make this work, so I have to double this whole reaction here, and then add them, and I can get my redox reaction balanced. Now, in this case, it didn't give off chlorine gas because there's other reactions going on in there, and chlorine gas doesn't bubble out. But you can get a nasty surprise if you're dumping things together and a redox reaction goes. So in this case, what is oxidized? It's whatever lost electrons. So this would be the one that's oxidized, and this is the one that's reduced. An oxidizing agent oxidizes something else and is itself reduced. A reducing agent reduces something else and is itself oxidized. I'm not going to worry about oxidizing agent and reducing agent. If something oxidizes something else, it's always the opposite. But losing electrons is oil. Oxidation is losing electrons. So this is oxidation, that's reduction. Now, I showed one of the classes this. Sometimes you could put reactants together in different conditions, you'll get different results. If I take cold test tubes and cold metal zinc and cold nitric acid and I put them together, they will react to make zinc nitrate and hydrogen gas. This is a single replacement reaction. This is what you would probably predict. One time I was in front of a class of students and did this, and I didn't have things cold. It was probably my first year of teaching. This is what I expected, and this is what happened. which was create the ruckus in front of a classroom of students. If the nitric acid is concentrated and this goes, it gets hotter as it goes, because this reaction is exothermic. We probably need to talk about some thermochemistry this year, since we didn't get to it last year. And it starts to get hot, then this reaction starts to go. And you get zinc hydroxide, zinc 2 hydroxide, that'll be zinc hydroxide, and nitrogen dioxide gas. It's a very toxic brown gas. It's the one we were making with when I was dissolving those cups, those little sterling silver cups. Many other reactions are possible also. The point is here to focus on the redox, which is, by the way, be careful around nitric acid because it'll do redox reactions and release that gas. When you go to do these, you have to work the problems out with pencil. You don't watch me do it and write it down. That is not going to fly. We will not be able to do it. You have to do these in class on paper. In our case, we'll be getting them off screencast. We'll either be in class watching this, doing it, or at home watching this, doing it. You can't learn it from the weekly notes. Normally, students can. If you take sulfur trioxide gas, for example, and put it with water, it makes sulfuric acid. If you look at the oxidation numbers, this is not a redox reaction because oxygen, if you look at the oxidation number rules, back here on table 2, page 696, oxygen is usually -2. I don't know which rule that is. Hydrogen is +1. I can't tell by looking at it which rule that is. Usually. Rule 2 would work for that. So, oxidation, number of oxygen is -2. Hydrogen's +1 and +1, so that has to be neutral. Oxygen's -2, -2, -2. This sulfur has to be +6. If you look over here, oxygen's -2, -2, -2, -2. Hydrogen's +1, +1. The sulfur has to be 6, +1, +1. All that has to be 0. So basically I'm -2, -2, -2, -2 for those 4 oxygen. This all has to equal 0. Hydrogen is +1, +1. What's the sulfur? And there's 1 of them. Well, it's got to be +6. Nothing here changes oxidation number, so this is not redox. It's just standard old, balance it the way you know how. This one, this decomposition reaction, is redox. If you take potassium nitrate and heat it up, you get oxygen out, potassium nitrite. This is redox. It's a decomposition reaction, but it's also redox. If I use the rule, and I think it's rule 2 that says potassium's oxidation number is equal to the charge it would have if it were an ion, potassium is all the way to the left in the +1 column, and oxygen is 2, negative. I've got -2, -2, -2, +1. This has to be +5 for nitrogen. If I do the same thing up here, I got -2, -2, +1. This has to be +3. And some of the oxygen is changing oxidation number while other oxygen does not. So nitrogen's gone from +5 to +3. You could say it's gaining 2 electrons, so that's reduced. Some of the oxygen is losing electrons, going from -2 to 0, and is oxidized. So you can write it as an electronic equation. Nitrogen's going from +5 to +3, that takes 2 electrons, it's reduced. Oxygen is going from -2 to 0, that releases electrons, so it's oxidized. If there's 2 oxygen at -2 apiece, I have to give up 4 electrons. Okay, here's another one. Okay, this is a single replacement reaction. Back when we did activity series, we may have made some copper. Well, we probably didn't make copper oxide. But if you had some oxidized copper and you reduced it with hydrogen gas, heated it up with hydrogen gas, you could turn it into copper metal and get water off of there. Now you can probably balance that one without any trouble, but a lot of redox reactions you can't. In this case, I've got hydrogen going from, you have to go through and assign oxidation numbers. So I'm assuming you're gonna have to, get on the curve here. Make sure you know how to do it. Anything that is in its elemental form, oxidation number is 0. That's like the first oxidation number rule. You should have those out. Have them half memorized. Oxygen's usually -2. That means since they're 1 to 1, copper's got to be +2. Over here, copper's going to its elemental form, so it's 0. Oxygen's still 2 minus, hydrogen's 1 positive, because +1 and +1 -2, that's 0. So hydrogen is going positive, losing electrons, so that's oxidation. Copper is gaining electrons, that's reduction. So it's a single replacement reaction to do this, but it's also redox. If we have copper gain 2 electrons, it goes to copper metal. Have hydrogen lose 2 electrons, H2 lose 2 electrons. We have to hydrogens that have a +1 oxidation number. I should probably have a +1 charge here, even though that hydrogen is not ionic. Okay, so it's page 34. I should treat this as an H+. Writing it that way. So I'll go fix that, hopefully. All right, so we studied the activity series. All activity series reactions are redox reactions also. So if you look at this figure, you'll notice how we're going from metals, lithium on down, and less reactive. Let's not worry about the halogens right now. This is the same as the table of reduction potentials. So this is page 293, figure 13. We did this last year with that lab on activity series. If you look at this reduction potential lab on page 712, it starts with lithium and goes to the less reactive metals the same way. This will help you determine if a redox reaction is possible and how aggressive it might be. Okay, let me go just a little bit further. Both these tables indicate what's going on. Zinc's higher in the activity series and is a stronger reducing agent. And there's numbers in there that tell you to do the math, how much the difference is. But if you put the numbers in, it'll show you that this should go. If you put copper metal in with zinc sulfate, it won't go. But if you put zinc metal in with copper sulfate, it will go. That's what that table is for you to plug numbers in and calculate that. Zinc is higher on the activity series than copper metal is, so it's a stronger reducing agent. So it'll go this way, but not the other way. If zinc is a reducing agent, then it is oxidized, and you write it this way, copper is reduced. Okay, I don't need to do that example. Just showing you chlorine, this works for halogens also. One's oxidized, one's reduced. If you take hydrogen peroxide with hydrogen peroxide, one of those molecules acts as a reducing agent, one of them acts as an oxidizing agent. Okay, now we're going to get into balancing reactions. There are two methods. You can use the oxidation number method or the half reaction method. Both work. Oxidation number method is simpler. We're not going to do that one though, because the half reaction method can be used in reactions that are in an acidic environment or a basic environment, so we're only going to do that one. Both have their strengths, but the half reaction method, there's some steps for it in table 6, and I've got them laid out step by step here, is what's going to work for what we're doing. And we're going to walk through page 695, example problem 5. And these, if you work in a base environment, you can add hydroxide and water. If you work in an acid environment, you can add hydronium ions and water. I'm going to change hydronium ions to hydrogen ions.